Hi guys, welcome back to Data Every Day. Today we are looking at a dataset of financial news headlines. We can't actually see the preview, it's not loading, but we're going to perform sentiment analysis on the headlines. We're going to try to predict the sentiment, which will be either negative, neutral, or positive of a given headline based only on the text. So this will be a natural language processing task. We're going to use a TensorFlow recurrent neural network to make our predictions. We'll also be using word embeddings. So one of the benefits of using word embeddings is that you have to do minimal pre-processing on the actual text themselves, because the model learns representations of the words. So a lot of the associations that the model makes with the words is actually learned in the network itself. Alright, so I'm going to import NumPy and pandas just for working with the data. And then for pre-processing, we're going to use the tokenizer and pad sequences function from Keras, and the train test split function from sklearn. Then for the model, like I said, we'll be using TensorFlow. So let's go ahead and import all of that, and we can load in the data using pandas.read.csv. Now we can get the file path for the CSV file up here, alldata.csv. Let me just zoom in a little so you can see this nicer. I'll paste this in, and we can take a look. Okay, so we got an error. Sometimes you'll get this error when loading a CSV file. Just go in and set the encoding to Latin 1, and that will work. Now, this particular CSV file did not have column names at the top, so what you can do is go in here and set names equal to a list of the column names you'd like. So why don't we call this the label, and over here we'll have the text. Alright, so here's our data set. Essentially what we have is a headline and a text label that's either negative, neutral, or positive. So what we want to do is feed this into our network after we've processed it in a way that works for the network, and then use this as the target we're trying to predict. So let's just make sure we have no missing values, although I doubt there would be any in this kind of data set. Sure enough, we do not. And we'll begin. So, pre-processing. We can also take a look at what kind of label values we have. Sorry, not df, it's data. So get the unique values in the label column. We have negative, neutral, and positive. Okay, so let's create a function called preprocess inputs, and we're going to pass in a data frame. This is going to create a copy of the data frame, and at the end we'll return the data frame. So right now this is just going to make a copy of what we have. So let's say, I guess I'll call it X. It will be the processed version of the data. So I'm going to pass data into preprocess inputs. Right now X is just a copy, but now we're going to make our modifications up here. Okay, so if we're going to feed this text into the model, it has to be in a numeric form of some sort. So the most common way to do this will be to encode each word as its own integer, and then feed the integers in some sort of encoded manner. So one way we can do this is with the Keras tokenizer, which is a very nice way. I'm going to create a separate function called getSequences that's going to do the tokenization of the sentences for us. So this will take in some text, which will be it could be a list or a pandas column. We're going to pass in the text column here, so that's what text is, and we're going to create a tokenizer object from Keras. And the tokenizer basically looks at a sentence. Well, actually, it will look at a bunch of sentences, and it will count up all. It will take into account all the unique words in the corpus of text that you pass in, and it looks at the frequency of these words. So first, it performs a bunch of preliminary pre-processing steps. It will remove all punctuation. It will lowercase all the words, and then it will split on white space. So you'll get more similarities between the words, but it's not absolutely essential that we process it perfectly because, like I said, we're using word embeddings, which will learn similarities between words. Now, right, so we use tokenizer.fitOnTexts to do this. It will take in the texts, it will count up all of the unique words, and then it will sort them in order of frequency. So the most common word will be assigned an integer of 1, the second most common word will be assigned an integer of 2, and so on. And then it will create a word index. So if we do this, if we return tokenizer.wordIndex, like this, just an attribute, and we call this function on, our text column, this is the word index it returns. So the most common words have these low-valued integers, and as the words get less common, you have higher values. Now, maybe if we want to increase the performance of this model, we may encode all the numbers as just a word called number, or just remove the numbers, because you can see the numbers are coming up quite frequently. But I'm not going to do that for this video. So you can see we have ranked all of the words, and if we get the length of this, we can see how many unique words we have. So we have 10,122 unique words in the whole text column, and this is a very reasonable number. Having a high number here can sometimes slow down the model. So it's good if you are using a body of text with a very large number of unique words, you can actually cap it with num words in the tokenizer construction. Like we could cap it at 10,000, and then it would only take into account the 10,000 most common words. But I'm not going to do that since we are dealing with a good number of words. So to actually perform the transformations, we're going to use tokenizer.texts to sequences, and then we're going to pass in the texts here, and we'll store the result in sequences. And I will actually return this for now so we can see what that does. And so it actually went in, and well, it's hard to see it, but we have a bunch of lists. You can see it's a list of lists, where each list in the list is a sentence. So this here is a sentence. Well, this is actually it's displaying the whole thing. But each one of these integers is a different word in the sentence. And now we have a numeric representation of each sentence in each headline in our data. Now now comes the issue of encoding. We need the model to understand the relationships between these integers. And you could do a sparse encoding or a one-hot encoding, where you have I think we had 10,000 or so unique words. So you could have a vector of length 10,000 with all zeros and a single one in the place of the word that you have. And so this would be sort of wasteful memory-wise to have 10,000 length, a vector of length 10,000 for each word. So the other way to do it is with a dense encoding, and that involves basically taking some high-dimensional vector space of your choosing. I think in this video we'll use 128-dimensional vector space, and we send each word to its own location in this vector space. And a vector in 128-dimensional vector space it has a length of 128. So it's a much lower memory way of encoding the words than a sparse or one-hot encoding. The other good thing about using this is called word embedding, is that where to send the word is actually learned by the model. We don't have to do it ourselves. So for that we'll use a Keras embedding layer, and before we do that, I want all of these sequences to be of uniform length, Right now they're all of different lengths. We have some short headlines, some long headlines. So we can pad the sequences using the pad sequences function from Keras. So this will take in some sequences. And we want to set the maximum length, or the length we'd like to pad to. So what we should use as the maximum length is the length of the longest sequence. So we can get that well, there's a few ways we can do it, but one way is we take the sequences and we can apply a lambda function to it. So I'll map a function here. The function is going to take x, which is a given sequence, and return the length of x. And we're going to apply that to every sequence in sequences. Then we'll turn this map object into a list, and we'll take the max of this list with numpy.max. So this will return the maximum length of a given sequence. We'll store that in max sequence length. And why don't we print it out so we can see how long it is. Maximum sequence length. So we'll pass in max sequence length. And then down here, when we pad it, we pass in max sequence length as our maximum length. And I'll also include padding equals post. You could do pre or post. Post means the zeros. Alright, we're padding with zeros. The zeros will go on the end. And I also want to return how long our vocabulary length is. So that 10,122, I think it was. So let's print out vocab length. And this is going to be given by the length of the word index that we saw before. So tokenizer.wordIndex. However, we are adding zeros with the pad sequences function, so there is one extra character. So it's going to be tokenized the length plus 1. That will be the 1 corresponds to the 0. Okay, and then let's pad the sequences, store that back in sequences, and see how it goes. Alright, so let's pass this in, and you can see we have now 10,123. The extra 1 comes from these zeros that we've padded with. And the maximum sequence length is 71. So all of these have now been padded to length 71, and there's zeros if the headline is shorter than that. So now we have uniform length inputs, and we can pass this array straight into TensorFlow. Then after we pass it in, these unique integers will be embedded using the embedding layer, like I described. So let's okay, let's get the shape of this. I want to see the shape of our inputs, and it is, so we have 48,000 sequences, just like this. Each sequence has been encoded to a vector of, or a list of length 71, where each element of the list is a word encoded as an integer. So we'll use this get sequences function down here. So we'll get the sequences like so. We'll pass in the data frame's text column. And then I want to get the labels. So TensorFlow requires that we pass in integer labels instead of text labels. So I'll create a mapping here. Call it label mapping. It's going to be a dictionary. And we'll map negative to 0. We'll map neutral to 1. And positive to 2. And then all we have to do to apply the mapping is call, we'll take the label column and call replace on it and pass in the dictionary. So this pandas function allows us to pass in a dictionary, and it will actually perform the mapping for as long as we specify all the values in there. And we'll store that in y. Y will be what we're trying to predict, in this case the sentiment. And the last thing I want to do is perform the train test split. So we'll use the train test split function from sklearn. That's going to take in what we want to split, in this case the sequences and our y. And we'll specify the size of our train set. I'll say 70% of the data. We'll turn shuffle on, which it's on by default, but it will shuffle all the headlines around before we make the split. And because there is some randomness involved there, I'm going to include a random state of 1. just to ensure that the shuffle and therefore the split is always done in the same way. Okay, and this is going to return 4 new sets of the data, train and test set for both the sequences and the Ys. So I guess I'll call it sequences, or I'll do train sequences and test sequences. And then we have our Y-train and Y-test. And I want to return these 4 sets of the data. So I'll get them back over here. We don't have X anymore. So let's take a look. I can remove this. Alright, and so these are our train sequences. And our Y-train should just be the numeric integer labels. So this means negative, this means neutral, and this means positive. Alright, so we're ready to begin training. So we want to take in our input and embed the words before we do anything else. So we'll create an input layer with tf.keras.input. We want to specify the shape of our input. The shape will just be the length of a single sequence. So we know it's a vector of length 71, which is a single one of these. And we can get that without hard coding it by typing train sequences.shape sub1. So the second dimension of the shape. Then we will get our embedding layer. I guess I'll just call it X with tf.keras.layers.embedding. So the embedding layer takes 3 arguments. An input dimension, an output dimension, and an input length. I'm not sure if you have to specify the input length explicitly, but we will. The input dimension is essentially what is the input space for a sparse encoding of your words, of your vocabulary. So like I said, if we wanted to encode each of these words in a sparse way, we would need a vector of length 10,123, and then we'd have a 1 in this case the 5,442nd place. We'd have a 1, and all the rest would be zeros. So any one of these words would be encoded in a vector of length 10,123. So this is our input dimension, like so. Now our output dimension is our choice. Basically, the higher dimension vector space you choose, the more complex patterns between the words you can capture. So I found 128 works quite well for this task. Or you could play around with this and find something that works. Now the input length is just 71. That's the same as this, so I'll just copy that over. Alright, so now this layer is going to take the inputs and learn embeddings for the words. It'll figure out where to send the words so that the loss is minimized. So we don't have to do that work. We pass in inputs, and then we get our recurrent neural network. And so a recurrent neural network is basically a way to learn long-term dependencies between the features. So if we just passed in one of these to a normal neural network, each word, you'd have 71 features, where each feature represents the word in a given place of the sentence. However, there's no way for the model then to understand the relationship between the features. It just knows, okay, the first word, the second word, the third word, all the way, and they're all independent of each other. Now, a recurrent neural network takes in each feature one by one, while also understanding the past, what words have come before. And there's multiple forms of recurrent neural networks. Then Lstm. Let me pull up a picture. Okay, here we go. So this is a standard recurrent neural network. Basically, I mean, it's a little low resolution. Let me see if I can. This one's a little better. basically, this is the input from the previous time step, and this is the word. So let me just look at this picture for now. This outputs, each time it outputs both a single output and the h sub t here is fed back into it, so in a loop. This is why it's recurrent, because it loops around. For each t, meaning time step, refers to each word. So as it sees a word, it takes in the new word, which is xt here, along with a history of the other words. So this h can be called the hidden state. It's basically a collection of memory about the sentence, about the previous inputs. So at each time step, it takes in a word, which is xt, and a vector representing the previous history of the sentence, which is ht minus 1. It goes through some sort of processing and then outputs an output and also feeds in the output to the next time step, which then loops around. So you can run this for each word in the sentence, and at the end, the output should have some sort of features that represent the information that you need extracted from the sentence. Now, an LSTM, a long short-term memory network, is it covers many of the issues with a regular RNN, and it's a more intuitive version. I mean, this one is very simple. The simple RNN doesn't have the power that an LSTM has. LSTM has a few features. It has this part. So let me explain. The ct minus 1 is called the cell state, and this is sort of a it loops back around and it flows through the whole thing. And each time, it's a bit of it is forgotten. So this is called the forget gate. You have some vector coming in from the previous time step. So both ht gets looped and ct gets looped. This is very complicated, so sorry if it's not making sense. But a sigmoid activation is applied to this vector coming through. And a sigmoid activation can take values, it sets values between 0 and 1. And so when we do this pointwise multiplication on the cell state with values between 0 and 1, it has the effect of forgetting some of the information in the cell state. Because either we can multiply by 0, which means forget it all, or multiply by 1, which means keep it all, or something in between. So we forget portions of the cell state at each iteration, and then we add new information taken from the hidden state. So you can just sort of think of this as we forget information and we add information, and each time what we forget and what we add is influenced by the next word, xt. And then at the end, our output is slightly modified by another tanh function with a sigmoid activation. So don't worry too much about the details here. Just sort of consider this as with each next word, it forgets some amount of information and adds new information. And then the GRU is sort of a simplified version of the LSTM. And the GRU also has a forget gate and a way to store a new memory. But it usually performs better on smaller datasets, and computationally it's usually faster. So we're going to use a GRU today. Sorry if that was a lengthy description, but we can get a GRU using tf.keras.layers.gru. And the GRU has, we pass in a number of units. This is just the same as a regular dense layer. How many neurons are you using? So essentially, each word will be connected to 256 neurons, and then those 256 neurons will be sent through the GRU unit that I just showed. And the output from the GRU after it goes through 71 time steps, one for each word, right? So it'll take in this, then it will loop, then it will take in this, then it will loop, then it will take in this, then it will loop, and it'll go through the whole sentence, and at the end, it will spit out an output that hopefully captures the information we needed to predict the sentiment. And we'll pass in the input from X here. I would also like to point out that this uses a tanh activation function, which significantly outperforms a ReLU. If you test it out, this is much faster and much more effective. So after the GRU, we will send it to our output layer, which will just be a dense layer with 3 neurons, where each neuron represents a class. So this will have a softmax activation, which will give each of these 3 values a value between 0 and 1, so that they all sum to 1, which will mean they will be the probability values for each class. So this will take in input from X, and then we'll create our model with tf.keras.model, pass in the inputs as inputs, and the outputs as outputs. Alright, then we'll compile the model. The optimizer here is an atom optimizer. Our loss function will be sparse categorical cross entropy, since it is a multi-class classification problem. And we'll just use accuracy as our metric. So we'll store the history of the fit in history and call model.fit. And we want to pass in the inputs now. So our inputs here are going to be the train sequences. And our labels are going to be ytrain. And we'll include a validation split. So we'll use 20% of the data for validation. We'll give it a batch size of 32. We'll train for 100 epochs, and I'll include a callback function, tf.keras.callbacks.early stopping. So this will just monitor the validation loss, and when it notices that the validation loss has not been improving for, we could say, 3 epochs, then it will stop the training and restore the weights from the best epoch. And that's all that will do. This way we don't have to keep adjusting and trying to stop it early ourselves. Alright, let's see how this goes. So module object is not callable. Oh, I didn't include dense. Sorry. It should be layers.dense here. There we go. Alright. And I would like to point out that when training GRUs, GPU acceleration improves the speed substantially. So I'm actually going to include turn on GPU acceleration. And that will restart the notebook, so give me 1 second. Alright, I'm running the notebook once more with GPU acceleration turned on. Alright, and it's going much faster now. It's watching the validation loss, and when it starts decreasing, when it starts increasing again, looks like it's increasing now, it'll stop after 3 epochs of increasing, and restore the weights from the best epoch. So we can check the results with model.evaluate. We'll evaluate on test sequences and compare the results to ytest. And we have an accuracy of 58%. So not so great. I mean, it's still better than a random guess. What's our class distribution looking like? We could take a look with value counts. Oh, it's a NumPy array. Okay, so, oh, sorry, this should be ytest actually. Alright, so we have not too many negatives. Most of them are neutral. But it's still better than a random guess, I believe. Actually, I'm not sure about that. Our baseline model, if we predict neutral every time, if we do 850 divided by the total, alright, so this is actually just as good as a random guess. Sorry, not a random guess. This is this is basically just predicting neutral for every example, so it's not doing very well. One way that we can really improve the performance is by actually, there's an option up here called return sequences. And this is set to false by default. Basically what this does, like I said, it will go through all the time steps in the GRU and then spit out the final output. Now if we turn this on to true, at each time step it will return an output. And it will return a two-dimensional array of the outputs from each time step if we set return sequences to true. And there's a lot more information captured this way. So usually this will give you better performance. The only thing is, once we set this, the output becomes two-dimensional instead of one-dimensional, and so we need to include a flatten layer to get it back into one dimension. So I'll pass in x here, and that will just flatten the two-dimensional output into a single vector, and we can then train again. And we should get better results here. Alright, it's looking better. Alright, and we get a accuracy of 74%, so a significant improvement. Yeah, and so, I mean, this isn't perfect. I'm sure we could do some more things to improve the model, mess around with the architecture a little more, maybe do some preliminary pre-processing on the text. But this will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.